So, the, so I'm Marc Eberhard from University of Washington. My talk's a little bit different, which is that if you look at all the work that's been done, presented here and a lot of other places, these problems are so complex when you look at networks, everyone ends up simplifying things. You have to. You can't do every single aspect of everything. And we're not going to do it either, of course. But the simple question we're kind of asking ourselves and trying to make some progress in is saying, well, where is really the uncertainty coming from? What are the aspects that you're modeling that are really important, and some of the things you can maybe get away with without changing your solution too much. And so I want to thank the various sponsors that have been here along the way. So what we want to do is look at the different contributions of parameters to the result. And so then you want to select what parameters you're going to focus on. And of course, it matters, first of all, how important is the parameter. You also care about how hard it is to get that parameter. And then the third thing is how hard is it to use that parameter, right? So they're all things which go into how you should be doing network analysis. And then also other things we want to contribute to the Near Sim-centered tools, because that's really important for the future of doing any of these kind of analyses. So everyone kind of does the same thing. You have ground motions, you have site location, you have some kind of inventory, you have some kind of model for it, you have some kind of damage coming from that model, you get a bunch of probabilistic results coming out of it. Then someone has to make a decision. What happens? Bridge close, open, and then of course after that there's all kinds of impacts that come out of it, which are quite important in terms of determining the impact of it. And every single one of these is complex. Everyone has all kinds of uncertainties. We're not going to solve it all. We're not going to have the perfect model. But what we want to do essentially is go through that loop enough times to get a sense of how each of these little pictures contribute. And it's not perfect, but we're trying to make some progress. And the idea, of course, is in a real solution where you're actually trying to affect the future, the idea is you'll be doing this analysis, making some changes to the inventory, and then seeing what the improvements are in terms of impacts to society. So the total problem is really complicated, right? So in terms of ground motion, the effect of ground motions, we have this set of motions. There's 30 that have been done already by our USGS colleagues. They're physics-based realizations, very similar to the stuff that Reno has done, except not at the same level of we can't get anywhere to 15 hertz or like they've done so far. But it provides 30 simulations, and we're doing another set of, or they're doing another set of 50. So we can look essentially at the event variability. Every single one of those is an M9 earthquake off the coast of the Olympic Peninsula, but different assumptions on exactly how that earthquake appears. And then of course we have the site conditions. And for site conditions, the model itself right now has a velocity, gives you results at 600 meters per second, and then we're going to propagate that up. And then of course the question is, well, do you know anything about the site? Do you know the site class? Do you know a sub-site class? Do you know VS30? Do you know the actual soil profile? Each of those decisions involve different levels of uncertainty, and each of those methods also give you a different amount of work. If you have to get the site profile at every single bridge, we're talking about a massive investment of capabilities. And so what we've done is taken a bunch of profiles that have been put together by Audie et al. At UCLA, which are essentially hundreds of profiles from the Northwest. And we've picked them in different categories, and we've picked different sets of profiles, and you can see the uncertainties you have by going through knowing nothing, knowing the site class, or knowing the actual profile. And then there's an enormous amount of uncertainty in the inventory. You can see work that's prevented earlier. You have people with Google Maps and going, not Google Maps, but Street View, going around and getting properties of bridges. You can go to the NBI. Everyone has access to the NBI. What we've done is we've gone in two locations. One is Puget Sound, the major highways, and the other one is Olympic Peninsula, where we're actually getting the properties of every single bridge in that location. And by that we mean we go back to structural plans, you get the column dimensions and the reinforcement, all that kind of stuff, the height of the columns, all the things you might care about, shear keys and all that. And the idea, of course, then is to compare What happens if you know NBI? What happens if you really know the details of the bridge? To what extent does that matter? And of course, everything matters, right? The question is, can we quantify how much it's going to matter? So we've done the detailed properties for about 750 bridges. And now part of what we're doing is trying to not only say, do I know the details of the bridge? Do I know the NBI stuff? Or can I use some kind of machine learning tool or some other tool to say, if I know these NBI parameters, can I predict the details of that bridge? There's really kind of three approaches you could imagine using for that. And you can do all kinds of statistics on trying to predict bridge properties based on what's already in the NBI set. So obviously age of construction, of course, is part of it. The structural superstructure is in the NBI. That's going to tell you a lot about what kind of shear keys are going to be in it. We know things like whether it crosses water or a road, whether it's an overpass or underpass. It turns out that allows you to make predictions about things like column heights. So you can imagine taking all the NBI data, trying to predict the properties of the bridge, because the NBI data doesn't really provide you much that you care about in terms of earthquake stuff. The models, we have stick models with all the things bouncing into each other. We've done so far 15 different kinds of models. Each model runs thousands of cases for different simulations, different soil types, different soil profiles, and you get this huge database of outcomes. And you can imagine either using the actual model, using some kind of surrogate, using fragility curves, going back to HAZIS if you want to, and just kind of see how do all these results affect what's going on. And then here's one example for one particular bridge type. You actually have to read this plot from right to left. On the right, you have the output of a bunch of different simulations. We're keeping track in the middle of the number of simulations with each bin. And then, of course, you can develop a fragility curve with the associated statistics for that. And so that's for one particular bridge. And the question, of course, is do you use the model? Do you use the actual, do you use a fragility curve? Or do you use a fragility curve for groups of bridges or for an individual bridge? At each place, there's different levels of uncertainty that are going to come into it. For damage, we're looking both at the columns and the abutments. They're really the only two. We've assumed there's no unseating. That's a big assumption. We're assuming no liquefaction, which is why I didn't want anyone to ask me questions about liquefaction. And so between the shear key damage and the column damage, we capture most of what's happened. Those also have uncertainty. And then as one example here, here's a result of a lot of results from the city of Port Angeles, which is on the northern tip of Olympic Peninsula. It faces Canada. And what's weird, if you look at the spectral, the acceleration spectra there, you can see that there's a baseline one plus the ones for different soil types, C2 being the stiffest, D3 being the softest we look at. And you get kind of predictable trends in the spectra. And there's kind of a basin there, so you get even this kind of two-humped behavior, which is very different than what we expect in design. And if you look at that second hump, it has quite a bit of effect. And then I purposely didn't provide all the details, but essentially for every soil type, for thousands of motions for every location, you can predict the likelihood of getting, in this case, to spalling of the columns. And not surprising, when you have a big basin in the soft soil, if you take the shear keys out, like you have in some bridges, then all of a sudden the tall columns just start dancing really fast. So you get the kind of trends you expect, but of course, now we're doing this, we have the results for all 15 types, for all 4 soil classes, for 10 profiles per soil class. You can then start getting the likelihood of getting there based on your granularity. And the next thing, of course, is really important is that when you're looking at all this, there's a whole other uncertainty which so far we know very little about, is the so what question. So what happens when that bridge is damaged? How likely is that bridge going to be closed based on spalling, bar buckling, residual displacement? And so we're going to be doing some workshops with a number of DOTs just to try to get a better sense of what happens when you get that level of damage. That's a hard thing to look at. And then we're also going to be working with people from the healthcare side of this NSF project to look at what do people need after an earthquake. And I was looking at the work from the Los Angeles port, and there you're looking at delayed travel times and all that. On the Olympic Peninsula, you don't have the same levels of traffic, but you have really crappy bridges. So we're focusing on connectivity. Can you get to the hospital? Or it turns out dialysis centers turn out to be actually one of the big things, which I didn't know until this project. So we're going to take all these realizations, kind of output by output by output for each network, for each realization for a network, and ask questions like, how many people can get to dialysis? How many people can get to the hospital? And then the other part, which is harder, is the hospital also needs a bunch of stuff to actually operate. So you have to not only have people get to the hospital, but the hospital needs to be able to get stuff. Okay, so we've put together a lot of different properties. The things which we're doing now in the kind of short term is looking at to what extent can we take NBI data, the National Bridge Inventory, for those 750 bridges and predict the detailed outcomes. So being an old guy, I'm going to first of all try to do it just based on trends we expect. Old bridges have less transverse reinforcement. Some bridges, ramps have taller columns in the middle, but shorter columns on the ends. And then in parallel, we're going to do kind of a machine learning version of it. I like the old version because I can see what's going on. Machine learning, I'm sure we'll get a better result, but then it might be tailored to the Olympic or to Washington State database. Who knows where it goes to other databases. So we'll be working on that. Something we ran into, which we didn't expect at the beginning, is that there's way, way, way too many bridges that are not anywhere near the standard ones we look at. So there's bridges out there that have concrete superstructures, but timber bulkheads as their abutments. I'm pretty sure that doesn't show up in a lot of analyses. And then we have movable bridges. Movable bridges have been shown in past earthquakes. Turns out you have a bunch of machinery, the bridge moves, and doesn't move after the earthquake. So we have to figure out what to do with all the special cases, and part of my fear is the special cases may actually overwhelm all the typical cases. Liquefaction and landslides, we actually just got a small supplement with Brett Maurer on triggering. And the triggering part, I think we got pretty down and a lot of data there. But then the question, of course, what does that liquefaction actually do to the bridge? And that's a much harder thing to figure out. So we'll take a shot at it. I'm not sure how far we'll get in that. And then work with our colleagues in health sciences to look at the impact. What do people decide about the damage? What does the healthcare system really need? And then, of course, the last one is this idea of disparate impacts, which are there different populations on the Olympic Peninsula. How are they affected by the changes in the network? And then finally, we're going to implement this in R2D with some other software we put together. And I hope next year we'll have some more specific results. Thank you.